And we're back. Happy Thursday. Today we will continue on with our description, this time, of tools that we can use to characterize the shape of a distribution. But before we begin, a few administrative bits. Homework 2 is due this evening at 11:59 and 59 seconds, 1 second before midnight. Please make sure also you are keeping up with the reading. It's not a lot of pages, but I still would expect that you spend about an hour or more per day on this class. If you do so, it'll put a swagger in your step. You'll be confident and ready to go. So make sure you're reading every single day. So when we last left off, we talked about so-called joint distributions, and we used the table form of this occurrence of these complex events representing two measurements, random variables D for outcome of a die roll and C for the outcome of a coin flip. We showed that when you sum down the margin, you can compute the probability of a coin flip being heads or tails, or if you sum across the margin, you can compute the probability of the die roll being one of those outcomes 1 through 6. And so let's begin with a little bit of warm-up. Suppose we're going to play a game. You wager $1, and I, the house running the game, I wager $2. And for this game, I'm going to flip a fair coin, and you're going to guess heads or tails. And the semantics of the game are such that if you are correct in guessing the outcome of the coin, you get $2. If you lose, I keep your dollar. So you win $2 if you're correct. If you lose, I keep your dollar, you lose $1. So one question one might reasonably want to ask is how much would you win if you were to keep playing this game again and again and again? Well, let's think about this. So half the time we get a heads, so probability of heads is 0.5, 50%. So half the time you get $2. The other half of the time, probability of tails is 0.5, that's 50%. You get negative $1, meaning you lose $1. And so if we were to weight the money that we get, whether it's positive or negative, by the probability, that's 0.5 for half the time we get $2, plus a 0.5 half of the time we get negative $1. So that's 1 minus 0.5, or a total of 50 cents. And that's what we can expect to win if we play this game again and again and again over time. And so let's try this out in Matlab. So I will meet you in Matlab. So we're here in Matlab, and I took the stick breaking example that we had from before for the 6-sided die, and I modified it to mimic or simulate the flip of a fair coin. Now here I only have 2 stick weights because that corresponds to the heads outcome or the tails outcome, and I changed the labeling for the events. Now I'm going to add some convenience constants. I'm going to say heads equals 1 and tails equals 2. And I'm going to use these variables later to help me. And so I normalize the stick weights, and I select the high end and low end, and I set a random number generator between 0 and 1, and I check it against all the stick regions, and I have a selection. And so I've collapsed that part that implements the stick breaking since we've done that before. All right. So now I have my selection, and my selection on each round is either going to be heads or it's going to be tails. It's 1, I'll call that heads. 2, I'll call that tails, corresponding to the first section of the stick or the second section of the stick. So now I'm going to check to see if I have a heads, but I need the amount of winnings, right? So winnings is equal to starting out as 0. And so now I take a look at my selection. If selection is equal to heads, well, if your selection is equal to what the coin flip was, I shouldn't say heads, you're going to guess correctly. You're going to make a guess. And let's assume, for the sake of argument, each time your guess is a heads, right? So let's have something called your guess. Your guess. And then your guess, we're going to say it's heads. All right. So let's assume each time you guess heads. Now, we could absolutely implement this so that each time your guess is randomized. In fact, maybe we should do that, but we're not going to do that for now. Let's assume your guess is heads all the time. All right. So your guess is heads, and we're going to flip a coin, and you're going to guess heads every single time. All right. So let's take a look at this. So if the selection, if your guess is equal to the selection, then your winnings is equal to winnings plus $2. Okay. Else, that means your guess is not equal to the selection. That means your winnings is equal to the winnings minus $1. Okay. So there we go. So over a number of rounds, let's set that equal to, let's say you play this game 10 times. We'll see how this works out. So after that, we're going to take our winnings and we're going to calculate on average how much our winnings are over the course of this game. So we played num rounds many games, 10 of them. So now we're going to say, all right, average the winnings per game is equal to total winnings over the number of rounds. All right. So now we're going to say message as printf, your winnings per game is %f. Now I'm thinking of C. Winnings per game. There we go. So now I display message, and we'll see what happens after 10 rounds of playing this game. So I run this. Winnings per game is minus 10 cents. Run it again, 20 cents, 10 cents, 80 cents, 50 cents, 80 cents, 20 cents, 80 cents, minus 10. So let's see what happens if we change num rounds to 50. So now we're going to play this game 50 times instead of 10 times. So now let's run this. 62, 86, 68, 26. So it's kind of jumping up and down, above and below 50, but it's a little bit better than going negative like we saw before. Let's try number of rounds is 500. It's a lot of rounds, and we'll see on average how much will you win per game. Let's try that out. So we save this and we run. Well, it's kind of closer to 50. It's plus or minus a little bit, kind of fluctuating up and down. Okay, interesting. So now let's try something like 5,000 games. That's quite a few games to play. But what we'll notice here is as we increase the number of rounds that we play this game, we see it's very close to 50. It's 50 plus or minus a very small amount. And so let's go back to the PowerPoint, meet you at the PowerPoint. And what we saw, as the number of rounds gets bigger and bigger and bigger, while from one round to the next, it might be a little bit above or below 50 cents, but the amount of wiggle, as it were, gets smaller and smaller and smaller as you increase the number of rounds. But moreover, if we play a really large number, in general, per game, we're going to win 50 cents. Sometimes you're up, sometimes you're down, but it all averages out to about 50 cents per game. So we try this in Matlab. And both the average value as well as how much this value varies above and below the average describes, in a sense, how this particular stochastic game or the system behaves. So let's think about these concepts a little bit more. And let's go to expectation and variance. So we said when we talked about random vectors, we said that you have multiple descriptors of things in the real world. And we gave an example of a joint distribution involving two random variables for the coin flip and the die roll. And often in practice, now that case was just two random variables. Imagine if we had 100 random variables. We had a vector of 100 different measurements. Now that table would be absolutely enormous, and it would be too much for us to write out the entire table of all the joint probabilities. It would just be too big. So often in practice, there are too many pieces of information for us to be practical to write out a complete accounting of the joint probability. So what's our solution then? Well, write down a summary instead of the whole table, and the summary will then describe the stochastic behavior so that anyone who's reading a description of your system will be able to understand it. And so these summaries that you compute, they're functions that you calculate over your observations. And these functions are so-called summary statistics because they're going to provide a compact description of the distribution. And these summary statistics we're going to talk about today are mean and variance. So when we talk about this idea of mean, we talk about the expectation, as in what do you expect will happen or what will happen on average. And we saw this with the game that we played. On average, it's 50 cents per game. Now, an expectation has a definition. It's defined as a kind of probabilistic average. And this probabilistic average is exactly what we saw or tried in this coin flip game. We weight the quantity of interest, the money that you get, whether it's $2 or minus $1, you weight it by the probability associated with the event of guessing correctly, the heads came up, or guessing incorrectly, the tails came up. Now, certainly, if we have a distribution of random observations, i.e., it's uniform, they all have the same probability, then the probabilistic average, this weighted probabilistic average, our expectation, is exactly the mean. Now, we note the mean or expectation as mu, lowercase mu, and functionally we write this expectation as mu equals the expectation of our random variable x, which is the sum, the weighted sum of all of the values of x, or our values, times the probability of that value. And so we write, if we have a uniform distribution, well, what does it mean to be uniform? It means to be random. All outcomes are equally likely. And so when we write that expectation, our probability, if all outcomes of n different possibilities are equally likely, that's just our value times 1 over n, where all the probabilities are 1 over n. So if we do that sum, well, we have 1 over n, x1 times 1 over n, plus x2 times 1 over n, dot, 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 plus times xn times 1 over n. That's just the sum divided by the number of observations. That is the average. And so the average is nothing more than the probabilistic average or the weighted sum when the probability is such that your system, your observations are random, equally likely probability. So this probabilistic average is our expectation, and this answers the question, on average, with a large number of trials, what is going to happen on average, or what do you expect to see? We also noted when we tried the coin experiment in Matlab that the number of trials, as it increased, that average got smaller and smaller and smaller. It wiggled above and below that 50 cents that we were looking for. And so something called the variance is another summary statistic. And the purpose of the variance is to explain how much a random variable's values are spread out in its distribution. What is the dispersion? Is it more dispersed or is it less dispersed? And when we talked about the example of two coin systems, we had the normal coin, which looked like this for 3 coin flips, and then we had a weird coin, which looked like this. And we said the first coin, system X, is better to bet on because you are more likely to guess a 1 or 2 heads out of 3 flips than you were a 2 or a 3, I should say. Let me correct that. A 1 or 2, that's correct. 1 or 2 heads in 3 flips versus a 0 or a 3 heads. And we said that the 1 and the 2 were 3/8 probability, and the 0 and the 3 were a 1/8 probability. Whereas here, we had all of them were 2/8 probability for the 0, the 1, the 2, and the 3 heads out of a 3 coin flip. And so if something is more dispersed, what the variance really tells you, it's easier to get something wrong if you're guessing something that varies very widely among a larger number of values. And as we see here, the coin system for the 3 coin flip on the right-hand side, it's easier to get something wrong. And so this variance then is a single number. It's a statistic, a function over data, and it tells you how much a random variable's values that it takes on are spread out, or how wide or how dispersed the distribution is. And so here we had that example. And this example, we said, you're better off betting on system X because it's not as spread out. If it's not as spread out, well, if you guess a 1 or a 2, you have a total of 3/8 chance each one to get it right, but only a 1/8 chance if you guess a 0 or a 3. In this case, for this coin system, you have a 2/8 chance, so you have 3 ways to get it wrong. So if you were going to guess either the 1 or the 2, you're more likely to get it right than if you were to guess using this Y coin system. And so this idea then, if we look at these two distributions, the variance of this distribution is wider than the variance of that distribution. It's less spread out, the probability mass over all the values that the random variable can take on. And so this variance talks about how much the random variable's values are spread out. Low variance means it's easier to predict the outcome because the probability mass is less spread out. So a fewer number of values or outcomes are going to be presenting themselves. If there are fewer alternatives, it's easier to get it right. Higher variance means it's harder to predict because the probability mass is more dispersed or spread out. So if you have more alternatives to choose from, it's more likely you're going to guess wrong, more ways to get it wrong. And so this idea then about spread out, what does spread out mean? How do we measure that mathematically? Spread out with respect to what? The center. So let's take a look at this. So the variance describes how much the values of a random variable that it takes on is spread out, or the dispersion. It's the average distance or spread between each of the random variable's outcomes that you observe and its mean. For the variance, you use symbol sigma squared. That's in contrast to mu, and it has to be sigma squared. And it's not just any average, it's the probabilistic average of the spread between each of the random variable's outcomes and its mean. So how we note variance sigma squared as a function with a variance of random variable x, and that's nothing more than the expectation of random variable x minus the expectation of x. Now the expectation of x, we just said before, this is mu, the mean, and we take that difference, the value of the random variable minus its mean, and we square that difference. And so if we're going to look at this as a weighted sum, this expectation, we sum each measurement, x, that's each outcome, that's a value, minus the mean, that's the mean, and we take that difference, we square it, and then we weight it by the probability that that random variable takes on that value. And we do that over all possible values, and we sum together those weighted sums of the square of the difference between the random variable's outcome and its mean, its center. And so these are the key parts. And the thing to pay attention here to is the square term. Now, the square term exists because we care about the difference, but we don't care about the direction. So we don't care if that measurement is less than the mean, or if that measurement that the random variable takes on is greater than the mean. All we care about is the magnitude, but not the direction. And so we square it for that reason. We're summing together the magnitudes of the differences, and we're weighting them based on the probability of which that particular value x will occur. Okay, so remember we talked about the spread, right? It can be above or below the mean. We saw that when we had that example. So the mean expectation for the coin flip game, when you bet $1 and I bet $2, was 50 cents. We calculated that. But for some practical experiments, sometimes when we ran the Matlab, it was below, sometimes it was above. And so we talked about this idea of spread being measured relative to the mean. And because the variance is the square of some unit, it can't really be compared against the measurement itself or the mean. So if you said something like, what is the average or the mean temperature? You'd say, oh, it was 64 degrees Fahrenheit. Okay. You could say, what was my measurement today, right now? Well, it was 61 degrees Fahrenheit. That's all degrees Fahrenheit. And so if you were going to talk about spread using variance, it kind of presents us a little bit of a problem. And it all comes because of this square term. Now, if you were talking about dollars, average money somebody made, you'd talk about 50 cents or $0.5. All right. Sometimes it varied. Sometimes it was $0.47. Now, of course, when you talk about this spread, you're going to have some value that's in dollars. You're going to have an average, a mean, that is in dollars. But when you subtract the two, the difference, you square it, that's dollars squared. And you're computing a weighted sum of the square of some quantity. So it's kind of hard to say, how dispersed was your money that you took home from playing this game? Oh, it was $100 squared. That doesn't make any sense. And so if you're going to talk about the spread, it's hard to talk about the spread and imagine how that compares to the mean or how that compares to a typical measurement, to be how much that value can vary in this direction or in that direction. And so this idea of trying to talk about things in the same units instead of dollars squared or degrees Fahrenheit squared, that doesn't make any sense. You can't really think about it. If you were to ask me, gosh, well, Dr. Holness, should I wear a jacket? How much is the temperature going to vary today? And I said, oh, it's going to vary by 75 degrees squared. You wouldn't know what to do with that. I wouldn't. So there's a fix-up to this, and it's called the standard deviation. Because variance measures as the square of some unit, it can't really be compared easily against the mean or some measurement. So it's kind of hard to think about what to do. So we talked about this idea about spread above and below the center. And so the standard deviation is the spread that we can use to make the comparisons between this measurement of the dispersion, the spread of a distribution, and either the mean or measurements that you would actually encounter, or the mean or the measurements that you would actually encounter. And so the standard deviation can be computed. Standard deviation's notation is sigma. Now you notice it's sigma and not sigma squared, lowercase sigma, as a function standard of x. It's nothing more than the square root of the variance of that random variable. And so our standard deviation now takes our dollar squared or degrees Fahrenheit squared, and it turns it into just dollars. And now we can talk about spread relative to the mean without trying to warp our mind around this idea of dollars squared or Fahrenheit squared. So now it's the same unit, or standard deviation, as either a measurement or the mean, the center measurement that we expect or on average we'll see. All right. So oftentimes in probability, we have different names for things, and I just like to make you conversant with the names because it's useful to be able to go out and read the literature and understand what they're talking about. So here, when we have a distribution, oftentimes we talk about the mean in the literature as being the location parameter. And as such, the mean tells you where the center of the distribution sits. And so if we had a distribution that looked like this, and mu was the center, well, if the center changed, that means we would shift the distribution to be centered at some other value. And so this mean is sometimes called the location parameter, and this standard deviation is often called the scale parameter because it tells you how flattened out, how dispersed it is. Something that has a small scale would be very narrow and peaked. Something that has a large scale would be more flat and spread out. It's almost like you took some material like peanut butter and you just kind of smeared the same amount of peanut butter over a large area. It's going to be thinner. If you smear that peanut butter in a very small space, it's going to be much taller. In similar fashion, we have our location parameter that tells you where the center is, and we have our scale parameter that tells you how spread out or how dispersed it is. And it just so happens that if you take a probability distribution for a random variable or any distribution, and you go plus or minus the mean, some proportion of your standard deviation, you're going to find a certain percentage of your probability lies within that range. And so if we take your mean, mu, plus or minus 1.96 standard deviations, that's going to represent 95% of your probability. So if you were to actually sum up the probability mass from the mean minus 1.96 standard deviations up to the mean plus 1.96 standard deviation, and you sum together all those probability masses, that'll sum to 0.95 for a total of 95% of the total probability. And there are standard other measures, and we use this to do something called outlier detection. It's a really powerful mechanism. It also governs how spam detection works. But nonetheless, we can take this mean and variance and standard deviation, and now we have tools that can compactly summarize this idea of where the typical values reside for distribution and what the dispersion is, how easy or hard it is to get it right if you were to guess. All right, so measurements are also often coupled together. You change one measurement and the other measurement also changes some amount. So that means they vary together. So let's take, for example, apples. If you were to look at the color of an apple, well, it's kind of red, kind of brown, kind of green, kind of yellow. You take the texture or the pattern of variation of color, well, it kind of splotchy, right? You have some red that goes to dark red, light red in a certain pattern. And if you take the shape, it's kind of roundish, right? Some are more round than others, some are less round, but nonetheless, they're all some kind of variation of round. So these all vary together. So you have certain color that comes with a certain shape, and that's what it means to be an apple. So covariance, not variance, but covariance describes the way that two random variables spread around their center, one influencing the other. And so here we have two graphs. On the bottom left, we have on the horizontal axis economic growth, and on the vertical axis, we have stock market returns. So if you look at these sample points here, these data points, well, for a certain increase in economic growth, let's kind of draw that increase in economic growth, you have a commensurate unit step increase in stock market returns. And so you'll notice, for the most part, as your economic growth increases, you go to the left here, to the right here, the stock market return goes up. So they're coupled. So some unit step increase in economic growth is going to be associated with a unit step increase in stock market return. And so that kind of makes sense because the more economic growth, the more products are being made, the more consumption, the more salaries. So the stock market, these companies are going to do better. The stocks increase in value, and you have positive stock market returns. Let's take this other example on the right-hand bottom side of the slide. Along the horizontal axis, you have world oil production. And on the vertical axis, you have gasoline prices. Now, let's think about this. If there's more oil availability, well, supply and demand would dictate that gasoline would be cheaper. Gasoline is made from oil. So if we trace these points, these data points, going from left to right, well, let's see. We have some unit step increase in oil production from here to here. We have some unit step decrease in gas production. Okay, So let's try from here to the next point. You have some unit step increase in oil production. You have some unit step decrease in gas production. All right. Well, let's look at that. So that seems to persist. So there's a coupling here in the negative direction. If you increase world oil production, some amount of delta in that direction, the gas price decreases some delta going down. And so here we have a unit step decrease. In the previous example, we have a unit step increase. So there's a positive influence between the economic growth and stock market return, and there's a negative influence between an increase in oil production and gas prices. And so how we measure this is with the covariance. We mark this as cov, x, y, the two random variables or measurements involved. It's the expectation of the product of two things. And we have the difference between measurement x and its mean, mu, I'll say mu sub x. That's the expectation of x. We take that and we multiply it by another difference, which is the difference in measurement y and its expectation or mean. So we have the product of the differences between two variables and their respective expectations. So if we were to do this out mathematically, we have a double summation because we're summing over all instantiations of random variable x and random variable y. We multiply the difference between measurement x and its center, the difference between y and its center, and then we weight that by the joint probability that x and y values will occur. And that is covariance, and that is the average way that two random variables will spread around the center. And how those differences in spread, what it measures is the coupling. A unit step increase or decrease in one results in a unit step increase or decrease in another. And that is our covariance. And that's another statistic that is a nice summary, so-called summary statistic, of the behavior of our distribution, the distribution that's coupled between two random variables. Now, certainly there's a linear algebra method for doing covariance. You get a covariance matrix, but at this juncture for this course, we're only going to talk about two variables. All right. So when we compare variables that have two different distributions, we need a normalized way to compare them. Instead of saying the covariance of, say, 123 for the covariance of one joint distribution and 34.7 is the covariance of others, it's often useful or helpful when you're comparing the coupling between two random variables. It's often useful to express them on something that looks like a percentage scale. And this percentage increase, for example, if we were to look at the units for covariance, we have for economic growth, we have a percentage increase for the economic growth, and then we have for stock market return, dollars. And so if we were to look at the units for this economic growth curve, we'd say percentage increase times dollars. If we were to look at the units for covariance for the coupling between world oil production and gas prices, we'd say barrels of oil for oil production and dollars. So barrel dollars or percent dollars. That doesn't really make sense. And so if we were to compare the coupling of this graph with the coupling of that graph, there's not really a good way to compare them unless you had some normalizing way to do that, the same way a percentage normalizes increases or decreases in some quantity. And so instead of saying these weird units and these numbers, it's helpful to express them on a percentage scale, and that percentage is the proportion of total spread that is contributed by the coupling between the two variables of interest. So that is called correlation. And correlation is the normalized or the percentage scale expression of the linkage between two random variables. And so correlation is written as Greek letter rho, lowercase rho, and that's nothing more than the covariance between x and y divided by the standard deviation of x and the standard deviation of y. So in essence, we take this coupling, that's the covariance, and we divide by the deviation for each one of those variables separately. Now, what is left is that proportion resulting from the coupling between them. So there's the variance in one, the variance in another, and then there's the coupling between them. And so this is essentially a rescaled version of the covariance. That's our correlation. And so so-called perfect correlation connotes or means or corresponds to the situation where the same unit step increase in one results in a unit step increase of another. So if we had economic growth of 1%, and that meant a stock market return of $1 or similar amount, that's a 1-to-1 or 45-degree angle when we look at the rise over the run. And so that's so-called perfect correlation in the positive direction, which is a +1 for this correlation score or this statistic. And then the converse of that is negative correlation, the negative 45-degree line. So a unit step increase in one is a commensurate same unit step decrease in another, or we have a 45-degree line sloping in the other direction. And that's a correlation corresponding to correlation of -1. And that's perfect correlation. So our correlation score is going to vary, rho is going to be in the real number line between +1 and -1. Anything in between is less than perfect correlation. All right, so that's all I had to say for today. As usual, please stay healthy, please stay safe, and I will see you all on Tuesday.